Good morning, everyone. Welcome to this class. So today we will start a new topic, Minimax and alpha-beta pruning. This is really new because actually until last class, what we have learned, all these models, they belong to the machine learning models, right? So there are some very classical machine learning models in the first half of the semester, like the naive Bayes, KNN, K-means, classical machine learning. After that, we go into the neural networks. Neural networks, they are also a type of machine learning models like the MLP and CNN. But for the Minimax and alpha-beta pruning, they are not machine learning, but they are still AI. So recall that in the introduction class, actually we introduced that machine learning is a subfield of AI, right? So that means actually there are some AI models that are not machine learning, like Minimax and alpha-beta pruning. It's just some types of AI algorithm while they are not machine learning. Actually, these are very traditional AI algorithms, and they belong to a big category of the AI algorithm, which is called the search algorithm. In search algorithm, for COMP2211, we will only learn these two search algorithms, the Minimax and the alpha-beta pruning. Actually, there are many more other search algorithms. If you are interested, actually you will learn more search algorithm in COMP3211 later on if you want to take that course. 3211 will focus much on the search algorithm. That's some traditional AI. But in this one, we will only see these two. All right, so search algorithm that, of course, is used to solve some search problems. Basically, a search problem is that there are many states. And we know there is a state which is the goal state. And what we want is to reach that goal state. Usually, you can imagine that there is an AI model, or we call it an agent. The agent just doing some search in all the states until it reaches the goal state. This is the search problem. And in order to solve the search problem, we can propose many different search algorithms. And specifically for Minimax and alpha-beta pruning, they are used to solve one type of search problem that is called game. Actually, the game, all the games, literally that's games. You play the games, actually they can all be formulated as some search problem. So just imagine that when you are playing a game, for example, you are playing some video games in your smartphones or in your computers, actually what you want to reach is a goal state, right? Usually the goal state is that you want to win. You want to win. The winning state is already a goal state. That is, when you reach that goal state, actually the game terminates, and also you will achieve a large number of scores to win the games. So the game is already a search problem. So in this class, we will just try to solve the games, which actually now we regard it as some search problems. The games, we won't cover too complicated games. So in this class, we only cover tic-tac-toe, a very simple game. Just use it as an example to illustrate how to write some AI programs to play the games. So you will learn how to implement an AI model for a two-player game, tic-tac-toe. The AI agent actually just makes use of some search strategies to optimally play the game, and we will introduce two of them. First, we will introduce the brute force, which is called the Minimax. Brute force here refers to like straightforward methods of solving a problem. Basically, is that enumerating all of the possible states and then to choose the optimal way. Then we will try to improve this brute force, because the brute force, referring to this name, you will know that it's very computationally expensive to do this kind of thing. So later on, we will also try to improve it to introduce the Minimax with alpha-beta pruning. Know that both of these two strategies, they are optimal strategies. So they will optimal play the game. So that means as long as the AI leverages any of these two algorithms, then the AI can reach some optimal results. And the same AI strategies actually can also be applied to other two-player games. Even though we use tic-tac-toe as an example, but actually it can be applied to other games, two-player games, of course. For example, the Connect 4, the chess, checkers, backgammon, etc. So it's some general algorithm to play the two-player games. So games, they are the oldest, most well-studied domain in AI. Because they are fun, right? Human like playing games. I think it's some like natural things for human. Like we just like play games, and actually games have some other good properties. Games, they are very easy to represent. Each game state, actually we can try to use some symbol or try to use some mathematics to represent. And for the games, usually the rules are very clear. As long as the rules are clear, then we can try to encode them, try to program them. And for the games, we know that the possible combination of the move can be very big. So for example, if we consider the chess, actually there are 10 power of 154 possible moves in chess. So that means for humans, we cannot enumerate all the possible combination of games. Usually for humans play the game, we cannot see some long-term goal, right? We can just, like for example, possibly we can just calculate for like 2 moves, for 3 moves, but when it gets further, actually humans cannot, because they are so big search space. But AI is very suitable to do this kind of thing, because AI has very large memory and AI computes very fast. So for games, AI usually can play very good, because AI can search in such a big search space. And games, they are like the real world in that the decisions have to be made and time is important. Usually when you're playing the games, there is some time limit, right? You cannot take infinite time to decide your next move. Since the time is very important, then actually we are more motivated to use AI to play games, because AI is much faster than human. And the games, it's very easy to evaluate the AI model. It's very easy to determine when a program is doing well or not. Basically, that we just let the AI program to play the games and to see whether the AI wins or loses. And then we can directly determine whether the AI plays well or not. So it's very easy to determine. Just playing the games and there will be some results. These are the reasons why actually games is a so popular and so well-studied domain in AI. And there are different types of games if we consider different aspects. First, we can try to divide the games into perfect and imperfect information game. Perfect means that the player, they knows all the possible moves of himself or herself and the opponents and their results. So all the moves are already known by the players. And imperfect game means that now possibly the player does not know all the possible moves of the opponent. Some information are hidden. Then that's called imperfect. This is the first aspect to divide the games. Second aspect, we consider the results. Consider whether the results can allow for cooperation. Then we can divide into zero-sum and non-zero-sum game. Zero-sum game are very intuitive, right? That means basically now there are 2-player game. And one player's gain is equal to the other player's loss on any given play of the game, because the sum of the 2 players' scores will be 0. So if one player wins, then the other player definitely loses. That's a zero-sum game. There are some other game, non-zero-sum game. In non-zero-sum game, again, some 2 players game. Now, the player's gain is not necessarily equal to the other player's loss on any given play of the game. In the non-zero-sum game, actually the 2 players, possibly they will choose to cooperate with each other, because it's possible to achieve some win-win results, double win results. But zero-sum game definitely is a competitive game. The 2 players will definitely compete with each other. They cannot cooperate, because if they cooperate, basically they help the others to win. And we can also divide the games into deterministic and non-deterministic games, depending on whether there are some random choices. The deterministic game is that the game does not involve any random choices. All the results are deterministic. When you play an action, then definitely it leads to the result. The result is already deterministic. But for non-deterministic, there's some games that involve some random choices. Now, the randomness is involved in such games. Not all the action results are deterministic. So this will be the different types of games. And there are some examples. In our class, we will use tic-tac-toe as an example because of the good properties. Tic-tac-toe is perfect information game, right? All players knows the moves previously made by all other players, and other players actually they know what are the possible moves in the future of the other players because it's just 3x3 game board and all the moves are quite clear by all the players. And tic-tac-toe is a zero-sum game. Tic-tac-toe, we know 2 players play the game. If player 1 wins, then she can score 1, and then player 2 who loses will score -1, for example. Actually, you can change the score like to 2 and -2. It doesn't matter, but that's some zero-sum game. If the game ends in a draw, then both players score 0. So that's some zero-sum game. The 2 players, they can never reach some win-win state. It must be one win, another lose, or there is a draw in the game. It's deterministic game. Deterministic because there is no random choices, there is no randomness. When one player plays a move, then definitely the move is there, no randomness at all. So this is a tic-tac-toe. You can also try to explain the others. For example, you can try to imagine that why the chess is perfect information, zero-sum and deterministic game, and why the Monopoly is perfect information, non-zero-sum and non-deterministic game, and poker, this is another popular game. Poker is not perfect information game, but still poker is some zero-sum game and it's not deterministic game. So you can try to explain the others, of course, given that you know how to play these games. Alright, so these are the different types of the games. And specifically, we consider the tic-tac-toe game. Tic-tac-toe game, also called the noughts and crosses, is a very easy game. Basically, if you have a paper, you have a pencil, then you can play the game. Of course, you also need someone to play the game with you. Okay. So for this game, the game board is just, as you can see, a 3x3 game board. You can just simply draw it. And the rule is that the 2 players, they will take turn to play a move in this game board. And the player who succeeds in placing 3 of their marks in a diagonal or horizontal or vertical line is the winner. So as long as one player first occupies one line, this line can be diagonal, can be horizontal, and can be vertical. As long as one player first occupies one line, then the player just wins the game. So for example, this is a simulation of the tic-tac-toe game. Suppose the cross starts first, and the cross just put the mark here. Next turn would be the knot, and then the knot just puts the mark here. And then the next move, cross put the mark here. Then, of course, the next move, the knot have to put here to prevent the cross from winning, right? Must occupy this cell. And after that, the cross just play here to prevent the knots from winning. The knots will just soon get a line. And then the knot have to play here to prevent the cross from winning. And at the end, the cross can put here, and then the cross just wins the game because the cross occupies one horizontal line. So this is the rule of the tic-tac-toe game. So until now, any questions regarding the games? Also, any question regarding how to play the tic-tac-toe? Yeah, it's very important. Before we learn Minimax and alpha-beta pruning, you have to know how to play tic-tac-toe, right? Otherwise, you don't know how the AI performs well or not. Great, now we all know how to play tic-tac-toe. Then the next step not to play with each other. Next step is that we need to implement some AI to play the tic-tac-toe. So let's first see a very naive approach. This is a naive approach. It's not optimal. Just consider the easiest AI to play this game. First, if there is a move that will win the game, then just play it. This is reasonable, right? If the AI can win, then definitely the AI should play that move. If not, then let AI check if there is a move that will block a win from the opposing player. If so, then place marker in the blocking spot. Also reasonable, right? Definitely the AI should also prevent the opponent from winning. But next, if none of the two cases happen, none of the two conditions satisfied, it's very naive AI, the AI does not know how to play, then otherwise just place the marker in a random empty cell. So this is to take some random action. That's why we call it a naive AI. Basically, the AI can only play if there is a direct win or there is a direct blocking from the other's win. But in other cases, the AI does not know how to play. So know that if the AI just runs in this naive approach, then the AI may not play optimally. Actually, it's not an optimal algorithm. You can just try to simulate by yourself. There are many cases that the AI just can't reach the best results. The AI may not achieve the best results if just do this naive approach. So even though this is an AI to play the game, but it's not good, right? It cannot perform very well. Then we have to think about how to improve the AI, because now we want some optimal algorithm. We want that, make sure that, okay, if the AI is used to play tic-tac-toe, the AI can win the game. Then we try a Minimax algorithm. So the motivation is that, okay, now that if the AI plays randomly, definitely the AI cannot get the best results. Okay, then just do the brute force. Brute force search is that enumerate all the possible states of the game. Just enumerate. So at the beginning, a player can choose any of the non-available empty spaces on the game board, right? At the beginning, we just construct a game tree like that, and the root node is the initial state. There are non-possible actions. So we just expand the root node into non-children nodes, as you can see, represent the non-different choices, non-possible moves. After that, we expand the tree, further expand the tree. So consider this node. So this node here. So after the cross, put the mark here, then there are 8 possible choices for the node, because the node can still occupy another 8 empty cells. So we further expand this node into 8 children nodes. And so on and so forth. For each node, we just expand it by considering all the possible choices of the opponent. And after that, like for this node, we can further expand it into 7 children nodes, because now there are 7 empty cells for the cross to occupy. Just expand that, and so on and so forth. We just starting from the empty game board, the initial state, expand the complete game tree, enumerate all of the possible game states until we reach the termination. Termination is that any player wins a game or there is a draw. That means when the game ends, then it's a terminating state. So we just enumerate all the possible states. As you can see, actually it will be super big tree if you want to complete such a game tree. Let's see how many states are there. The first action, there are non-possible choices, right? Non-empty cells. And then the second action, that is the second layer. This layer, we count how many nodes are here. We find that the second layer actually has 9 times 8, which is 72 nodes. Because for each of the non-possible first choices, we have 8 possible remaining choices. And then for the third action, that's the third layer in this tree, there will be 9 times 8 times 7 number of nodes. Because for each of the 72 previous choices, we have 7 possible remaining choices, and so on and so forth, until we consider the deepest level, the last level in this tree, last action, we will have non-factorial choices, this number of nodes. So that means we have, at the last layer, we have 362,880 leaf nodes at the last layer. Then we can count the total number of states, right? So just we add all of these nodes up. And then this is the last layer, this number of nodes. This is the second layer until we get the first layer. And in total, we find that in this game tree, except from the root node. So here we didn't count the root node. But of course, it's OK that you just add another one. It doesn't matter so much for the root node. So the total number of states, that's the total number of non-root nodes in this game tree is 986,000. This number of nodes. This is a very, very big number, right? If you want to enumerate all of the game states, you need so many nodes, so many states. But note that this is just some rough estimation. This is not accurate because actually we don't need so many states. Some of the states, they are illegal. Consider that actually the game can end before there is no more empty space on the board. Right? As long as one player wins the game, then basically we reach the termination state. So actually, at that case, you don't need to further expand any of the termination state. But in this calculation, we just count that from the root node until all of the cells are occupied. We count all the possibilities, but some of the possibilities, they're just illegal for the game states because the game can just end before that. Then actually we can just delete some of the nodes. That means, but still, after we delete some of the nodes, there is still a huge search space. Then how to determine which move to take based on the current game state if you have such a super big game tree? The answer is to use Minimax to perform such brute force search. So let's see what is Minimax. Minimax is a recursive algorithm. I believe you already know what is recursive if you have learned some of the programming courses or some of the algorithm courses. Recursive means that the algorithm will recursively call itself. This is a recursive algorithm. And Minimax is used to choose an optimal move for a player, assuming that the other player is also playing optimally. So in Minimax, the agent will always assume that the other player also plays optimally. We'll always assume that actually the other player is also applying the optimal search strategy. And in the Minimax can only deal with two-player game, by the way. Actually, the Minimax can only deal with the zero-sum games. In this case, we have two players, and we call them maximizer, denoted as max, and minimizer, denoted as min. Just call the two players these names. Of course, these are not only names. Actually, the two names already indicate how the two players will perform the game. So maximizer, then by this name we know, seems that this player is trying to maximize something. And minimizer, this min player, seems that this player will minimize something. Then what is this thing? Actually, this is a score. This is a scoring method. We need to define it. For this game, we need to define a scoring method from the standpoint of the max player. So that is, for this thing, for this specific score, actually it defines as the score of the max player. And then everything makes sense now. Of course, the maximizer will definitely want to maximize this score. But the minimizer will definitely want to minimize this score because this score represents the max player's score. And this is a zero-sum game. To minimize the maximizer score is equivalent with maximizer minimizer player's score. So that's why they are called max and min. And the maximizer, you can consider that is some AI for the tic-tac-toe game, try to maximize the score, while the minimizer try to minimize the score of the AI. Of course, this is just one of the possible, we use it to illustrate, but it also applies if you reverse the two players. For example, you can also imagine that the human is maximizer, AI is minimizer, it doesn't matter. And this algorithm is called Minimax because it helps in minimizing that the other player can forces us to receive. So that means for the max, you can just imagine that you are a max player. The things that you are maximizing actually already minimized by your opponents. What you want to maximize is the score that already minimized by the opponent. And then for the minimizer, of course, the min player, what the min player minimizes, this score actually is already maximized by the maximizer. So basically, it's just the two players fight against each other, minimizing something and maximizing something. Actually, they are just like manipulating on the same score. So this is the concept of the minimax. And let's see what are the steps of the minimax algorithm. So consider that now we want to evaluate a node n in this game tree. Actually, we know that this node n is the root node. Usually that we want to evaluate a root node, right? And we want to select a best move for the root node. And what will we do? First, we construct a complete game tree below n. So that is starting from the root node n, you need to construct a complete game tree. Complete game tree that you need to consider all the possible actions of the two players until all the states are enumerated. All the possible game states are enumerated. All the leaf nodes in the complete game tree, there are some termination states. This is a complete game tree. And then apply the utility function to each terminal state. A utility function, here we define at the end, utility function is the numeric values given to the terminal states, and the utility function already decides what we said here. We need to define a scoring method from the standpoint of the max player, and this scoring method is exactly the utility function. Utility function, for example, in tic-tac-toe, we can define the utility function like this. We know that for all the game results, there are just three possibilities. First, the maximizer wins. Then we define the utility function as positive 1. If the maximizer loses, then the loss, we denote this game state as negative 1. If there is a draw, then the utility function will define it as 0. So there are only these three possibilities. Actually, all the terminal state, we can apply such utility function, right? All the terminal states, that's all the leaf nodes in such game tree, they must be the end of a game. And since it's already an end of the game, then we can apply such utility function. So we just use this utility function to give the value to each terminal state. All right, until the step 2, you have a complete game tree, and all the leaf nodes, they are already equipped with some values. But we still don't know which move to take at the root node, right? We need to decide what is the root node. That means even until now, we already see all the future, all the possibilities in the future. But still, we don't know what is the best move for the current, this root node. Next would be we will evaluate all the game states in such complete game tree and then decide the best action. So step 3, we will select a node that has not been evaluated yet, and all of its children have been evaluated. If the node is a max node means that now it's a max player's move. If it's a max mode, then the value is taken from the maximum of the children nodes. Because it's a max node, it's the max player's move. Then for the max player, definitely the max player should choose the move that will lead to the maximum possible value. So that's why its value is taken from the maximum of its children nodes. It wants to choose this move to get some higher score. But if it's a min node, that means now it's the min player's move. The min player wants to minimize the score, so the min player definitely will take the minimum of its children nodes. So we evaluate a node depending on these rules. And we will repeat this step 3. Repeat this step 3 until all nodes are evaluated. And if you observe this thing that we select the node that has not been evaluated yet, but all of its children have been evaluated. Basically means that at the beginning, all the leaf nodes, they are already evaluated, right? All the leaf nodes, actually their terminal states, their values are evaluated in step 2. And next, we need to select the second last level, because the second last level nodes, their children have been evaluated, and so on and so forth, until we reach the root nodes. But still you may ask, what is the specific order to evaluate all the nodes? We only see that we repeat step 3 until all the nodes are evaluated. This search order is depth first search. So the game tree search in Minimax will be done in some depth first search manner to find the value until the root node. Depth first search is used for traversing and searching the tree data structures. The algorithm always starts at the root node and explores as far as possible along each branch before backtracking. So it starts from the root node all the way until some leaf node and then do the backtracking. So this is a depth first search. It always follows the depth direction until it reaches some leaf node. So we just follow this depth first search order to evaluate all of the nodes in a game tree until step 4, we will evaluate all of the nodes. After that, the whole game tree is evaluated. So that means all the nodes, that means all the game states, they already have some values. The next thing is that we need to decide the action for the root node, right? Our beginning goal is we want to select a best action for the root node. So this will be done in step 5. For the node n, the root node n, we choose the minimax decision if n is a max node. So that means at the beginning, we want to select the best move for the max player, then just choose the move that leads to the highest value. The max wants to maximize the value. If n is a min node, that means if actually we are selecting some best move for the min player, then we just choose the move that leads to the lowest value to minimize this score. And this would be the steps of the Minimax algorithm. So it might be not so clear if we directly look at these algorithmic steps. Let's try to evaluate on an example. So suppose we want to select the move for the cross at this game state. The game state is that now the game is already like this. So as you can see, the cross already occupied these 3 cells and the knot already occupied these 3 cells. We want to decide, okay, what is the best move for the cross to play now? And then according to the Minimax, we need to construct a complete game tree. For now, it's the max move, the cross move, and after that, the knot, the cross can play these 3 possibilities. So because there are currently 3 remaining empty cells, the cross can put here, here, or here. So we expand this root node to these 3 children, and then this level 1 is the min node, right? It's the min player's move. So for each of the action cross has already played, the knot can take some further actions. So for example, the first branch here, after cross puts the mark here, the knots can still put here or here. And then level 2, the max move. So all these nodes, there are some max nodes, and then the max can put the mark, can only put the mark here, the cross. And until now, this is a terminal state. This terminal state is that there is a draw in the game. So we need to evaluate it using the utility function. So that's why this node has a value 0. This is directly from the utility function. And for this game state, if the knot just put here, then the knot wins the game. The knot is the minimizer, the min player. Then this game state, according to utility function, will have the value -1. And if the cross just plays here, then the value is +1 because the cross will win the game. The max wins, and so on and so forth. Actually, we can expand all the branches until we complete the whole game tree, until all the leaf nodes, there are some terminal states. And then we evaluate all the terminal states, that's all the leaf nodes in such game tree according to the utility function. After that, we need to perform the evaluation the depth first search evaluation along the whole game tree. So to make it clearer, I will just draw it in the whiteboard. But I will omit the game board, so I will just use some nodes to represent that. So now we have the root node is a max, and in total we have 4 layers. And this is the max node is here, and there are 3. All right, this is a game tree. Of course, all the game boards are just omitted here. I represent them using the nodes, but they are the same thing. All right, what we have done in the previous step is that we evaluate all the terminal states already using the utility function. So at least now we know that this node has a value 0, this node had a value +1, this node had a value 0, and for this node had a value +1. For this node, it had a value -1. This is what we already get. We evaluated all the terminal nodes. And next would be we need to start to do the evaluation for all these nodes and following the depth first search. Now that in the Minimax algorithm, we have a step it called that if the node is max node, then we will take the maximum value. If the node is a min node, we will take the minimum value. So basically that we always need to compare the node's value with some previous values, and to make it easier, especially later on when you want to program the Minimax algorithm, we will initialize all of the node values. And how to initialize them? To make sure that you can update for all the nodes correctly, it's better that we initialize the max node, all the max nodes with -infinity value, right? Because later on, the max node need to select the maximum from its children. So at the beginning, just initialize it as -infinity. Later on, when it meets some larger value, it can get updated. So for all these max nodes, we initialize them as -infinity. Then correspondingly, for the min nodes, of course, we should initialize it into the +infinity. Because for the min node, whenever later on it sees some smaller value, it will just get updated. So for the min node, initialize to +infinity. All right, initialization. Then let's start to do the depth first search. Depth first search is that starting from the root node. Go to the leftmost branch. This node hasn't been evaluated, and we have to go on to this node hasn't been evaluated. And actually, this is not leaf node, so go back to go to this leaf node. All right, until now we reach a terminal state, a leaf node. We cannot further expand it. This is already the end of this branch, and this node is a terminal node, so it's already been evaluated, has a value 0. So next is that it's backtracking. Backtrack to its parent node, to this max node. In the meantime, return the value 0 to the parent. Now this max node receives the value from its child. It receives a value 0, and this is a max node, right? The max node will always want to select some higher value. So it starts to do the updating from the -infinity to select the max between the old value, -infinity, and the new value it receives from its child, which is 0, just get the value from its child and will be updated to 0. So after that, this max node updated to 0, and this is the only node, only child node for this node. So that means for this node, all of its children already being evaluated, and the end value for this max node is 0. So actually, we finish evaluating this node. The value of this max node is 0. It received the value from its child node. All right, we need to continue the depth first search. So we need to backtrack to its parents, to this min node. Now this min node receives a value from its child, which is 0. So it will pass this value back to its parents. This is the min node. Then the min node needs to be updated. Whenever it receives some new value, it needs to be updated by selecting the minimum between the old value, positive infinity, and the new value it receives from its child, which is 0. So now it's updated as 0 for this min node. But note that for this node, the current value is 0. It's not a final value. It's some temporary value because there is another child for this node we haven't evaluated. So we continue the depth first search. For this node, we go to the second child, and this is a leaf node, so we have to go back, check, return to this parents, and with the new value -1. So after this min node receives another new value from its child, it do this update. So it should be updated from the mean between the old value, which is 0, and the new value it receives from another child, -1, so which is -1. So now the min node is updated as -1. And it finishes evaluating all of its children. So that means the final value of this min node should be -1. And we finish evaluating this min nodes. We backtrack to its parents. The parent is root node. So backtracking to the parent with the value -1. So the parent max node will do the updating. It's a max node, so it should be updated between the old value -infinity and the new value it receives from its child, -1, so which is -1. But we haven't finished yet. So there is some other branches for this node. So we continue the depth first search and goes to the second branch. Itself is already a leaf node, so we need to go backtrack to the parents with the new value +1. So this max node will further get updated to this one, the max between old value -1 and the new value it receives from its child, +1. So it's get updated to +1. And not finished yet because there is remaining branch. It goes to the third child. This node hasn't been evaluated yet, so continue until we reach some leaf node and go backtrack to its parent with the value +1. And this max node will get updated to the max between old value -infinity with the new value it just received from its child, +1. So the value should be +1. And this is the only child, right? The only child for this max node. So we finish evaluating it. The final value for this node should be +1. After that, go back to its parent. The parent is a min node. For the min node, it needs to be updated to the minimum between old value, +infinity, and the new value, +1, which is +1. This is a temporary value. We still have the very last branch to evaluate. So it goes this way according to depth first search, and then go backtrack to this max node. After that, this max node will be updated to 0 because it receives the 0 value from its child. And this is the only child. So we finish updating this max node. It received the value 0, and then go backtrack to the parent, which is a min node. So the min node will further get updated between the old value, +1, and the new value is received 0, which is 0. So that means for this min node, the final value will be 0 after we evaluating all of its children. And then go backtrack to the root node. So at the end, this max node will be updated to the max between old value is +1. The new value it received is 0, but the maximum is still +1. So that means actually it already have a better selection before. So until now, as you can see, we already finished all the backtracking in the depth first search. So starting from the root node, at the end, after we evaluate all the nodes, go back to the root node, and then we can conclude the final value for the max node should be +1. So all of these steps actually are the step 3 and step 4. Evaluate all the nodes in this complete game tree according to depth first search. And then we need to go into step 5, right? Step 5 is that now we need to choose the minimax decision. So that is, for this root node, which move should the cross play? We already see that, okay, the best value it can achieve is +1. Then is that we select the move that can lead to +1, and actually we find that it's just this move. So this is the optimal action for the cross to take at the current game state. So the minimax decision is to put the mark at this position, and actually that can directly win the game. So this is how to play the minimax if we use this tic-tac-toe as an example. So actually all the steps you can also see at the slides. But the slides, yes, may not be so have this some dynamic process. So I just show in the whiteboard, but they're still equivalent in these slides. You can see these steps. And after all these steps of updating, we finish the minimax and we get the best move for this cross. All right, so any question regarding the minimax algorithm? Great, if no question, then let's take a 5 minutes break. After that, we will continue. All right, let's come back to the class. So now we already see what is the steps of the Minimax and also how to apply the Minimax in some specific games in a tic-tac-toe. Basically, that's we need to work on some tree structure. That's the game tree. So actually, this is why we say that is just some search problem. You can consider that the search problem is that we always need to represent the search problem as some structure. Usually it's a tree structure, and then we need to apply some search algorithm. Like here we apply Minimax algorithm to search on a tree structure to find the goal state. Here the goal state is the terminal state with the maximum value decided by the utility function. This is the Minimax. Next would be how to implement the Minimax from scratch. Yes, for the Minimax and alpha beta pruning, we go back to the implementing from scratch. So actually in lab 9, you also need to do the implementation from scratch because we finished the neural network. Neural network is okay for you to just import the libraries to use the libraries, but for Minimax, very traditional AI, we go back to implementation from scratch. All right, but at least some of the functions is okay. Like for example, the utility functions to define the game, to implement the game. For this part, it's okay. Like we will provide this with you, but you need to implement some core part for the Minimax. This part is just some helper functions to draw the current state of the game. So for this draw board, basically that we want to draw this 3x3 game board. We print like the current state information, and then for these 9 cells, we know that in total we have 9 cells. So for I in this range 0 to 9, if what I is 0, we use different values to denote different board states. So if the value is 0, then that means it's an empty cell. In this case, we just draw this empty cell to indicate, okay, it's still not occupied. And if the value is 1, we use 1 to denote that it's the mark of AI or the mark of the cross, the max. In this case, we just put the cross mark at that position. If the value is -1, then it's the mark of humans or the mark of the nodes. So we just put the not here. And of course, it's a 3x3 game board. So whenever we have 3 cells, we need to change the line, go to the next line. So if I plus 1 is divisible by 3, then we need to change the line, go to the next line. And so this is just a helper function to draw the board game. And next would be the check game. Check game is that we need to check if there is a player wins. And then we will return different values for different game states. So if the human player wins, we directly return -1. Actually, that's our utility function, right? If the AI wins a game, we return 1 utility function. If there is a draw, then we return 0. So all of these 3 cases, we return the utility function. So to indicate the value of the terminal state, but there is another case that if the game is not finished. In this case, we use another value. We use 2 to represent, okay, this is still going on game, so the game is not finished yet. So check game. Yeah, I know somehow for this implementation it's a little bit ugly because we hard code all the winning patterns. So actually for tic-tac-toe, it's a very simple game. So in total, we just have 8 possible winning patterns. We directly hard code. The first winning pattern is that if any player occupies 0, 1, 2, that's the first row, then that player wins. The second is the second row, so on and so forth. In total, we just have these 8 possible winning patterns, so we hard code all of them. The winning positions, we use a list to add all of these 8 winning patterns. And then we just check all the possible winning patterns for each player. For I in range 0 to 8, this range is for all the winning patterns. In total, we have 8 winning patterns. We check whether the cell is non-empty and whether the winning positions are with the same mark. So if the board winning position I0 is not 0, then that means it's not empty, right? And we find that all these 3 cells in the same winning pattern is occupied by the same player. So basically that the marks in these 3 positions are the same. And then we need to return who wins the game. So we return the board with the winning positions mark. So we know that if it returns 1, then that means actually here we already use 1 to represent is the mark of AI, so which actually coincides with the utility function. So here we can directly return this one. But if after running the whole for loop, it's not finished yet. So if the cost reach here, then it means that no player wins yet. And still there are 2 possible cases. The first is the game is not finished. So if any element is 0, so any cell is still empty, then that means the game can still going on. So we return 2. This means the game not finished yet. Otherwise, finally we can return 0. If the code reach here, and that means no one wins the game. In the meantime, all the cells, they are already occupied. So that means there is a draw, the game draws. So we need to return 0, the utility function for draw game states. So this function, another helper function to check the game results. And this is another function to obtain the user's input and update the board. So the human turn, we let the human player to input the nodes position. It can be from 1 to 9. And then if the board post -1 is not 0, then that means this position is already occupied. So we need to print illegal move and then terminate the program because it's an illegal action. Otherwise, the move is legal, then we can put the mark, human mark, which is -1. We put the mark at this position. Let the board post -I be -1. By the way, the post -I because we give the user the index from 1 to 9, but we know that in Python the index is from 0 to 8, so that's why we have -1 here. So this is how we get human turn. Alright, actually this is the core part of the Minimax algorithm. All of the previous functions, they're just helper functions to define what is a game. And next, for Minimax, this is implementation of the Minimax search. So it receives two arguments. The first is the board. The board is a current board. That means the current game state. And we know if we want to evaluate for this current game state, basically that this is our root node, right? We need to search below such root node. And the player is that who is the current player. It can be max or min. And then we define a global variable count. This is we want to record how many times we have called this Minimax algorithm. Minimax is a recursive algorithm. Recursive means that it will always try to recursively call itself, and here we just want to record how many times it recursively called itself. So whenever we call this Minimax, we will let count be added with 1. So just count how many times we called it. And then we first get the result. From the check game we previously implemented, we check if any player wins the game for now. If the result is not 2, and that means the game is already finished. So we just return the result because it's the end of the game, right? And note that this step, if we go back to the Minimax algorithm steps, this step is exactly evaluating all the terminal states. If the result is not 2, then that means the board is already, the game state is already a terminal state. We need to use utility function to evaluate it. And what we return here is exactly the utility function. The result can be 1 if the winner is AI, can be -1 if the human is winner, or can be 0 if there is a draw. So what we return here is just a utility function for terminal states. And this is to check whether it's a terminal state and then return with the corresponding utility function. Okay. After that, we need to do some recursive recall. That means the depth first search to evaluate all of the other nodes. So we create an empty list, which is called scores. Then we check all the board locations. Note that check all the board locations is that we want to put the mark in the different cells. And we check all of them means that we will enumerate all of the possible actions that can be taken for this step. And this is already expanding the game tree. Expanding the game tree, that's starting from a node, we take all the possible next moves. So for all these board locations, if board I is 0, then that means the cell is empty. Empty means that now the player can put the mark there. So just let the board I be player, put the player's mark at this cell. And then we perform the Minimax for the next player and append a score to the list. So the scores will append with the Minimax with board player times -1. So what do we mean here? So of course, this is already a recursive call, right? So inside this one, we recursively call this function itself, Minimax, with the board. Note that the board is already changed. The board is not the same with this board because we already put the player marker at board I. So that means we already tried one action. And then we give the new board to the Minimax function and the other player. Because we always use 1 represent AI, -1 represent human. So here we just let the player be player times -1, means that now it's the opponent's move. And then we recursively call it. So we will use the Minimax to evaluate the tried node. After we take a move, it already expands the tree and go to the tried node. So here we evaluate tried nodes and append the scores here. Of course, this is only a try, right? We just want to attempt to put the marker here and to see what is the score. It's not that we really want to play here. So we undo the trial, let the board I be 0 again. After we evaluate, okay, what should be the resulting value, we undo the trial. We don't want to really put it here. We just want to evaluate it. So for all of the empty locations that we can put the mark here, we evaluate them inside this for loop. After that, after this for loop, actually we will finish evaluating all of the nodes. Because for this minimax recursive call, it means that starting from the root node board, the current game state, it will go all the way down until it reaches some leaf node. Right? Until it reaches some leaf node, it will return this result, the utility function here, and then it goes back to its parent to pass the value to the parent. So this would be exactly the depth first search until we reach the root node inside this for loop through this recursive call. At the end, we need to return the score. The score, of course, depends on who is the player. If the player is 1, that means the player is AI, the max player, we need to return the max of the scores. But if else, that means the player is human, is the minimizer, then we need to return the min scores. So this is the minimax. Basically, this part is what we have done previously in starting from a root node, expand the game tree, and then evaluate terminal states, evaluate all the parent nodes until we reach the root node, until we get the value for the root node. So this is the minimax. Next function is AI turn. For AI turn is that how to decide the move for this AI, for this max player. So this function just try to find the optimal action through the minimax value. The AI turn given a current board, the current game state, how to choose the move. So first let the position to be -1. So initialize the position to be some illegal value and initialize the game, the node value to -2. Actually, this is somehow different with what we have done, right? Here, for all the max nodes, actually we evaluate it to be -infinity. But it doesn't matter here because if we look at the utility function can only take 3 values, 1, -1, 0. So that means as long as you initialize the max with a value smaller than -1, is equivalent with initializing it as -infinity, because anyway it will get updated after it sees a higher value. So this, we just set it to be -2. Of course, you can set it to be -3, -4, -10. It doesn't matter as long as it's smaller than -1. They are all equivalent with -infinity. So it's the initialization for a max node. All right, then again, we try to put the mark at the empty cells. So for I in this range 0 to 9, all the board cells, if the board I is 0, if the cell is already empty, then we try to put the cross at this cell, let board I be 1, and then we can call the minimax function which we implemented just now. But this minimax, it can evaluate the node value according to minimax. So we let the score be the minimax board -1. So we calculate the minimax score for the human player. And then we undo the try, let board I be 0, because until now we haven't decided what is a move. We just want to try. And then we update the score for this max player, for this AI. If we find score is larger than max value, then that means, okay, this max node sees a higher value from its child. In this case, the max value should be updated as the score. And in this case, the current position is better than the previous choice. So let the position be I. So that means, okay, this is a good position. This is a good choice. After we run this for loop, it will examine all the possible actions for the AI. And each time, whenever it sees a higher score from its child, it will update the max node value into that score and selecting a better move. So at the end, after we run all these for loops, at the end, the score is already the maximum from its children. And the move, that's the position, is already the best move it can select. So at the end, we put the cross at the position is the best move. Let the board position be 1. And this position is exactly the minimax decision. Like here, the position will just select the second move. This is already the best move because it can get it into the maximum value from its children. This is the AI turn, how to perform the minimax action to select the best move. And then would be some main functions. Basically, let's construct the game. And actually, after you put all of these code cells into your Google Cloud, and you can play the game with the AI using Minimax. So first, the board is an empty game board. So all of these cells are just 0. All of them are empty. And then we can print some like game information. The computer is cross, and you, as a human player, is the not. And you can also select whether you want to play first or not. Then for this game running, is that for I in this range 0 to 9. This is the maximum possible moves. Maximum possible turns play the game, because in total there are just 9 empty cells, so actually we can just play at most 9 turns. And first check the game whether it ends or not. If the check game board is not 2, then that means the game already ends, finished, then break because it's ended. Otherwise, take turns to play the game. Because actually the human already decides whether to play first or not, so we can always use this to decide whose turn it is now. So if it's AI's turn, then let AI turn take the board, the current game state, as an input, and then we'll run this thing. We'll run this function. Of course, for this function, it also needs to run the minimax, call this recursive algorithm. And then we can also print count to see that in order to decide for this move, how many times the AI recursively called the minimax algorithm. And else is the human turn. Let's just draw board and take a turn from the human. And after one move, we can again just check the game. And if the result is 0, then that means there is a draw. So just print the information. If the result is 1, then AI wins the game. So just print the AI wins. Otherwise, the human wins. So this would be how to implement the minimax algorithm for tic-tac-toe game. I don't know whether you tried this in your Google Cloud or not. Actually, you can try to play with AI. You will find that actually you can't beat the AI. So I think the best result you can get is to force the AI to a draw. Because the AI implemented in Minimax is already an optimal algorithm. So actually you cannot win such an optimal algorithm in playing tic-tac-toe. The best results we can get is just to have a game draw. All right, so any questions so far related with the implementation of Minimax? Okay, great. So for Lab 9, we will release it by today. So that, you can start to work on it, I think, starting from today. But of course, the alpha-beta pruning contents are not covered yet. We will cover it on next Tuesday. And since it's already the end of the semester, I know there are many deadlines for you. Lab 6 will be due next Monday. So if you haven't submitted Lab 6, please remember to submit your Lab 6 in time. And also at the end of the semester, we have PA2, we have Lab 8, we have Lab 9. So please manage your time properly. And if you really think that is somehow too overwhelming, actually don't forget that we only count the best 4 of your labs. The best 4. So if you already have full result, full scores for the previous labs, then it's okay. If you really feel too overwhelming, it's okay to give up Lab 8 or Lab 9 because we only count the best 4 for your lab results. So please manage your time properly. And also, it's not only you overwhelmed. Zinc is also overwhelmed during this very busy period. I know some of you received these results running the Zinc, like it says can't open some source files, some test scripts. It's not your fault. It's not your fault. Actually, it's because Zinc is very unstable, very overwhelming, crowded during this period because there are many deadlines. Not only COMP2211 is using Zinc, actually many other COMP courses, they also use Zinc. So that's why the Zinc it just get overwhelmed in this case. So in this case, the Zinc just unable to load the test Python files. That's the testing scripts. The overload problem, I don't know whether it's will get more stable because as I can see, there are like many deadlines in this period in our course, in other courses. But this problem is just temporary. That means if you ever meet such problem, maybe after a while you can try to resubmit your work, and then it will try to resubmit your work. So basically, that whenever you meet this problem, it means that it's Zinc problem, not your problem. And you can just try to regrade it, try to resubmit it maybe a few minutes later to see whether it works well. And if you have already submitted your work before, and if you already received your full marks previously, that is okay. Then that means you are expected to receive full marks for the public test cases as well. And don't be frightened by this one, by this error message. It's just Zinc problem. All right, so that's all for today's class. Remember to attend Lab 9 on next Monday or next Tuesday. That will be the last lab session in this semester, and I will see you on next Tuesday.